Okay, well, thank you for giving me the opportunity to speak to you again today. You worried me a little bit with the title of my talk. I thought I'd really mix things up, but I'm actually starting out with a question, and that's, how should we really define ultrafine particles, and why am I asking this? Well, if you look at our current regulatory standards on particulate matter, only PM10 and PM2.5 are regulatory standards. These are based on mass below certain cut points. As far as ultrafine particles go, there really is, by convention, we say, well, they're particles smaller than 100 nanometers. But what does that mean? Does it mean number, surface, mass, all? Does it mean classification aerodynamically or by mobility? We don't know that. Similarly, for nanoparticles, again, typically defined as particles smaller than 50 nanometers. Sometimes you see them defined as smaller than 10 nanometers. Are they, again, based on number, mass, surface, all? And again, questions about which diameter are you basing your sizing on? And the slide I'm showing you shows basically the sort of typical trimodal distribution you get from vehicle-related particles, showing different metrics, number, surface area, lung deposited surface area, and mass, and the lung deposition fraction. And you can see actually that the lung deposition fraction is very size dependent. And again, for ultrafines and nanoparticles, we're getting in the range with a very high lung deposition fraction. Now, why do we care about definition of ultrafine particles? Well, first, there's no clear epidemiological evidence linking adverse health effects to ultrafine particles. And we believe that at least is partly due to no universally agreed upon definition of ultrafine particles. If we look at common metrics, a number below 100 nanometers, or sometimes total particle number, is used, but the lower cut point, which can make quite a difference, is often not specified. Do we cut off at 10 nanometers, 3 nanometers, etc.? For mass, we see studies with upper aerodynamic cut points typically ranging sometimes 100 nanometers, sometimes 2, 3, etc. For surface area and also for lung deposited surface area, again, there's no real agreement on cut point and so on. Sometimes these metrics are well correlated, sometimes they're not correlated at all. So again, how do you interpret epidemiological evidence or other health effects? One thing to keep in mind, however, is that animal effects actually show that instilled surface area may be more closely associated with adverse biological response or mass, which we tend to mainly talk about. Now, I want to focus on on-road and near-road exposures, because those are where we get a very large fraction of our exposure to particle matter. The measurements near freeways have been going on since the early 70s, and this just shows some size distributions measured by a California roadway right before 1975. And basically, I've got surface area and number weighting. We've got measurements upstream and downstream of the roadway. And what you see, if you take the difference, you can get the number added by the roadway and the surface area added by the roadway. And notice everything here is well in this, well, sub 100 nanometer range in this case, and that we were getting very high concentrations of tiny particles back then. Jump forward about 30 years, and here are some more roadside measurements in California. And again, you see a similar modal structure. You see these are all downwind measurements. This is upwind, so the difference is what's being added by the roadway. And we've got different time of day, morning and afternoon. But again, you see the same sort of modal structure. The curved plots on the right are log scales, so just another way of looking at the data. Then we jump forward to nearly the present. This is a study done in North Carolina, again, doing upwind and downwind, but here they looked at downwind decay. They looked at summer experiments. They looked at winter experiments. Again, we see the modal structure. We see somewhat higher concentrations in the winter. When you look at the downwind experiments, what they did is they accounted for dilution as you move downwind. And this is a comparison between 10 meters and 150 meters. And the reduction from here to here is due to dilution. But this additional reduction is due to some kind of volatilization that they didn't explain in detail, again, suggesting the volatility of these particles. Now, I just wanted to put these in perspective. I said the structure is the same, but the concentrations aren't the same. If we look at the peak dN d log dp, that's only a rough measure because it depends on the breadth as well. But the peak in 75 was about 4.5 by 10 to the 6. In 2004, 2 by 10 to the 5, and 2018, 3.5 by 10 to the 4. So things are getting really a lot better, but this modal structure remains. And I think we're going to see this modal structure continuing out in the future, especially since more and more it's going to be old vehicles that are contributing to what we're breathing. Because as you just heard about the Euro 6, Euro 7 vehicles, they're near zero emitters. So we're mainly going to be breathing old vehicles and malfunctioning vehicles. Now, that brings us to our suggestion for new metrics. We are suggesting, and these are only suggestions, that we have 3 new metrics, N500, M500, and S500. These metrics represent total number, mass, and surface area below 500 nanometers, respectively. There's a question about what this 500 nanometers means, and we haven't really decided on that, whether it means by aerodynamic diameter or by mobility diameter. And there's a difference. Here is a sort of typical trimodal distribution, and by mobility diameter, below 500 nanometers captures this much. By aerodynamic diameter, below 500 nanometers captures all this. Again, whether you take aerodynamic or mobility, these metrics do effectively capture all number, surface, or mass. The N500 definition also should have a lower cut point, and we're suggesting for now that that lower cut point be 10 nanometers, although there are many, many instruments that go below that, so you'll have to be careful with the lower cut point. N500 that we're suggesting is not very different from the current definition of ultrafine particles. We're not suggesting that we throw away the current definition of ultrafine particles. So these new metrics, really they're intended for characterization of ambient exposures and linking them to acute and chronic health effects. They are not intended to be used for regulatory tailpipe measurements, although they might be useful in formulating new ambient regulatory standards to complement existing PM10 and PM2.5 standards. So then the next question comes, well, how would we measure these? Well, the idea of these new metrics is that we've come up with a standard for measurement, but to make any sense of this, you need lots of instruments out there. The best thing to do would be to measure size distributions. Then you could capture all the metrics. You can determine whether it's a surface problem, number problem, or mass problem. But these are pretty expensive instruments. On the other hand, as we heard earlier today, there's some prospect of new low-cost sizing instruments. And I think wide deployment of such instruments could be really exciting. Another way of going is single metrics. These are lower cost. For example, the typical, when we hear about ultrafines today, it's typically a condensation particle counter, but you can also measure number with modified diffusion chargers. Surface area also, or lung deposited surface area, either of these can be measured quite well with variations on diffusion chargers. Mass, for fast response measurements, there are instruments like the Ducati mass monitor that's used for engine measurements. It is a good mass monitor in real time. Or you could use traditional filter measurements, which could then be a PM 500 instead of PM 2.5. So those are my main recommendations or thoughts to consider on new metrics. But the next thing I want to briefly talk about is how should we be sampling from new engines. Now, I'm calling these non-regulatory sampling and dilution because I'm not talking about measuring total particles like we do for down to 10 or PM23 or whatever. I want to measure what we're breathing in the atmosphere. And these things are really hard to measure. I don't expect we'll have regulations very soon, but we still should be measuring them. And so there have been a lot of efforts to measure these particles, and a really good project that laid the groundwork for doing this was the European Particulates Project that developed a unique partial flow system, no transfer line, porous wall dilution, using the aging chamber, and it diluted at near ambient temperatures. It did a really good job of producing semi-volatile particles, and those are the particles we're breathing roadside. Now, just to convince you of that, on the left side here, I'm showing plots of on-road measurements we made some years ago where we ran measurements with and without a thermal denuder. This is without a thermal denuder, with a thermal denuder. Practically all the material in the nucleation mode was semi-volatile. Here's the volume with and without. A big fraction was semi-volatile. If you have semi-volatile material, it's going to be temperature dependent. Here's how the fraction in the nucleation mode varied with ambient temperature. Again, showing this is semi-volatile. So if we want to make measurements that represent roadside, we've got to measure the semi-volatile material. People over the years have come up with good systems. This is an example of using that system developed for the EU Particulates program, showing how sensitive dilution is, nucleation mode formation is to dilution temperature. This is some work we did in Minnesota. My colleague was PhD work showing the sensitivity to dilution ratio. So measuring semi-volatile particles, you have to be very careful. It's a very sensitive process. One of the things that people are getting wrong right to this day is with sampling lines. You can't have any kind of a long sample line if you're going to measure semi-volatile material. The plot on the left shows what happens when you got here less than 1/10 of a second residence time in the sample line and out to 2 seconds, and it completely wipes out the nucleation mode. Here, this blue curve here is the same dilution system that we used for this study here, but there are hardly any particles forming. Why? Because in this study, we were using a 70-meter sample line. In the earlier study, we're using 20 centimeters. It's a big deal. Okay, let me wrap up. Recommendations for non-regulatory sampling and dilution for semi-volatile particles. We recommend partial flow sampling, porous tube dilution, short heated transfer lines with short residence time, primary dilution ratio around 12, that tends to give you a big nucleation mode, and secondary dilution is necessary to be compatible with the instrument and freezing particle physics. Dilution to air temperature we should have at low, 25 degrees, both primary and secondary. Aging time around 2 seconds seems to give good consistent results. And as a practical matter, even though relative humidity makes a difference, it's just easier to use dry dilution air. And again, the last thing I want to say, and this is really important because I read paper after paper after paper where they're using heated dilution and say they're measuring semi-volatile particles. You're not. You maybe are measuring some fraction of semi-volatile particles. So thanks for listening.
Great. Thank you very much, David. I mean, it would have been interesting to hear what you had to say about concentrations of particles in hospital rooms, but I think this was really interesting, and thank you for taking this on. There are quite a few comments and questions in the Slido. So the first one is from Greg. He says, really nice to see the emphasis on ultrafines and the lack of standardization in the definition. Could upper and lower size limits be applied when measuring?
Yes, I think that's very important. That's where there is a lack of standardization. And that's why we're saying it makes sense. A 500 nanometer upper cut point really makes sense because it captures all the metrics we talk about, number, surface, and mass. A lower cut point doesn't make a lot of difference on anything but number, but it makes a big difference on number. As we know now, as we go from PN23 to PN10, that makes quite a difference. And there's some instruments now that go down to PN1. But as a practical matter, for now, we're suggesting that you count to 10 nanometers. Now, I think we're going to see a lot of variation on this, and this is just an interim suggestion.
Great. The next question is from Martin, and he asks, why do you want to limit number, LDSA or surface to below 500 nanometers? There's hardly anything above, unlike for mass.
Basically, we picked a common cut point of 500 nanometers because that metric captures the ultrafine component. There's a little bit of surface area above 500, but we were interested in the ultrafine component, so we cut there. But it's true. Most of the surface area, most of the number is already below 500, and maybe we don't need to be rigorous about saying putting that cut point there. But we felt for consistency, we should do it that way.
Great, thanks. Adam then asks, for new semi-volatile standards, shouldn't we focus on total semi-volatile particle mass? As semi-volatile materials is lipid soluble, it will ultimately dissolve in the body.
There's a lot of discussion of soluble, insoluble, water soluble, etc., on semi-volatile material, and I frankly am not in a position to really comment on the health effects of that, especially in the nucleation mode. But I should remind you that our PM mass standards on vehicles include semi-volatile material. So when we measure mass from any vehicle, when we do mass certification, that includes semi-volatiles.